Hello and welcome to the Sustainable Materials Management webinar series, a joint effort between the National Recycling Coalition and the Pennsylvania Recycling Market Center. My name is Wayne Bowen. I'm the program manager for the Recycling Market Center and will serve as your co-moderator today. Today's topic is titled Glass for a Sustainable Future, and our presenter is Dr. John Morrow, who I will introduce in a moment. After Dr. Morrow's presentation, Pete Previte from the Recycling Market Center will moderate the Q&A session. So if you have a question or comment, you can use the Q&A feature located on your control panel on your screen. Please note that an edited version of this webinar will be made available for viewing via YouTube links on the National Recycling Coalition and Pennsylvania Recycling Market Center websites. Dr. John Morrow is Dorothy Pate Enright Professor and Associate Head for Graduate Education in the Department of Materials Science and Engineering at the Pennsylvania State University. John earned a BS in Glass Engineering Science in 2001, a Bachelor's of Arts in Computer Science in 2001, and a PhD in Glass Science in 2006, all from Alfred University. He joined Corning Incorporated in 1999 and served in multiple roles there, including Senior Research Manager of the Glass Research Department. John is the inventor or co-inventor of several new glass compositions for Corning, including Corning Gorilla Glass products. And John joined the faculty at Penn State in 2017 and is currently a world-recognized expert in fundamental and applied glass science, statistical mechanics, computational and condensed matter physics, thermodynamics and kinetics, and the topology of disordered networks. John is the author of over 380 peer-reviewed publications and is the editor-in-chief of the Journal of American Ceramic Society. He is co-author of Fundamentals of Organic Glasses, 3rd edition, the definitive textbook on glass science and technology, and author of newly published textbook, Materials Kinetics, Transport and Rate Phenomena. John is a fellow of the National Academy of Inventors with 83 granted patents, and John is also a fellow of the American Ceramic Society and the Society of Glass Technology. He's a member of the National Academy of Engineering and World Academy of Ceramics. And I will hand it over to you, Dr. Morrow.
All right. Thank you so much, Wayne, for your kind introduction. And thanks to you and Pete and Bob for the invitation today. And thanks to everyone who is taking the time out of their afternoon or morning to join us. So my name is John Morrow, and I'm going to tell you a little bit about glass, sort of from a big picture point of view. I will give you some information on my own personal journey in glass and tell you about some of the exciting new research that we're doing in glass for a sustainable future in my group here at Penn State. Glass is a material that we often take for granted because it is something that we usually look through rather than looking at, whether it's looking through the windshield of our car, through the windows of our homes, or through the jars of our food or beverage packaging. Normally, we want to see what's on the other side. So it is less common for people to actually pay attention to the glass itself. And that's why I was so pleased to see this article published by The Atlantic recently, calling it Humankind's Most Important Material. Glass has changed the world like no other substance, but people usually overlook it. And more recently, earlier this year, we made the cover of National Geographic, declaring this to be the glass age, how cutting-edge technology is helping this ancient material reshape our future. And indeed, if you look at the history of humanity, oftentimes the great epics of our history are named after the materials that had the greatest influence, the Stone Age, the Bronze Age, the Iron Age. And there's a fairly compelling case to be made that we're now living in the Glass Age. So how is it that glass has played such a key role in helping to enable modern civilization and helping to create entire new fields of scientific discovery? In some cases, it's things that we often take for granted, like architectural windows. If you look especially at modern architecture, the big, beautiful windows that enable us to see outside, enable the natural sunlight to come in while providing a good thermal barrier to the outside, a good mechanical barrier, and strong corrosion resistance so it doesn't interact with rain. And windows have been transformational to modern architecture. Glass lenses for spectacles to help correct vision. Glass lenses used in telescopes as well. In fact, telescopes and the advent of glass lenses have been key for bringing astronomy into its modern era, where no longer do people have to rely on just the naked eye to study the stars, but they could use telescopes. Likewise with microscopes. So glass here was essential for the creation of the entire new field of microbiology, to the discovery of microorganisms, bacteria, viruses, and so on, the origin of diseases. All of this is thanks to glass. Glass is also prevalent in terms of packaging, whether it is beverages or food or cosmetics. Here, what I'm showing is actually a vial for the EpiPen cartridge that people carry around if they have any major allergies, for example, to bee stings. Here, the glass must be able to store the medicine and not react with it over a period of many years, and also provide good mechanical protection. Right now, we're all communicating through very thin strands of high purity glass called fiber optics. These strands of glass are about 100 microns in thickness, or about the same thickness as that of a human hair. And these are made out of the highest purity glass ever created by humankind. And the entire world is connected by fiber optics now. It runs across continents, it runs under oceans. This was really the key invention to bring us into the information age and enable the development of the internet. And it's not enough just to be able to transmit that information. We also need to be able to display it, whether it was the older cathode ray tubes, or these modern flat panel displays. Glass has been the medium of choice for displaying that information. And you'll find these large, thin pieces of highly engineered glass on all of your televisions, computer monitors, smartphone screens, and so on. And speaking of smartphones, glass is now not just something that we look through to see the information on the device. It's actually the primary interface by which we interact with these computers that we carry around in our pockets. So with a smartphone, no longer do we need a mouse or a keyboard, but you're touching the glass itself, and the glass needs to have the appropriate electrical, dielectric, and mechanical properties to be able to respond to your signal, and also prevent the introduction of damage due to scratching or indentation. And of course, glass is also key for all of transportation, whether it is cars or trains or planes. We need to be able to look out of the vehicles while at the same time keeping the drivers and the passengers safe from the outside. So glass has clearly played a huge role in bringing modern civilization to where it is today. I do believe we are just at the beginning, though, and there are many more future possibilities in store for glass in the coming decades. In the realm of information technology, we're starting to see foldable and even flexible displays. This is made possible by ultra-thin sheets of glass that are thinner than 100 microns. And when you make glass that thin, it can actually become bendable. High refractive index glass lenses are essential components for augmented reality glasses, where you can superimpose virtual images on top of the actual reality around you. Glass is also a promising medium for memory storage. Both IBM and Microsoft they have projects now using glass for high density three-dimensional memory storage that can store data at much higher densities and for much, much longer periods of time compared to conventional magnetic memory storage. And glass optical fibers are also going to be key for quantum communication. This is perfectly secure communication that is done by quantumly entangled photons to make it impossible for anyone to tap in and steal your information. When it comes for transportation and architecture, one of the key trends going forward is going to be autonomous vehicles. And if we have self-driving cars, then that opens up the possibilities for a lot more infotainment and information systems and screens on the interior of automobiles. Of course, all of these being touch-enabled as well. For the outside part of the car, glass windshields have not changed in a very long time, and there are new glass technologies available now that will enable thinner, lighter weight windshields and automotive glazing that can actually improve the mechanical performance of the windshields while also improving the fuel economy of vehicles by reducing their weight. When it comes to architecture, so the next generation of energy efficient architectural glazing is no longer going to have a noble gas between the two panes of the window, but instead actually have a vacuum pulled there, this so-called vacuum insulated glazing. This will improve the thermal efficiency of windows and help improve the energy efficiency of buildings. The problem is that if you pull a vacuum, though, that actually creates mechanical stresses that are on each of these panes of glass, and the glass needs to be able to withstand that fatigue behavior over the lifetime of the building itself. Glass is also being used in really remarkable ways throughout modern architecture, whether it is the Shard here in London or this somewhat scary glass bridge sticking out over the Grand Canyon in Arizona. Within people's homes, acoustic damping glass will be important for those living close to highways or living in a noisy city. Also, glass will help be a critical part of enabling this Internet of Things, bringing more touch connectivity and internet connectivity to devices and appliances throughout our homes. When it comes to renewable energy, so glass fibers are a critical part of windmill turbines. These are actually composite materials where the key material is fiberglass, and this fiberglass needs to have as high of a Young's modulus as possible to enable maximum stiffness of the windmill turbines. Windmills become more and more efficient the larger they are, but in order to make larger turbines, they need to have higher stiffness fiberglass. And so that is really key for wind energy. When it comes to solar energy, glass plays a role in a variety of ways. One is through photobioreactors, which convert sunlight into chemical energy through photosynthesis. And all of the algae here is being stored in glass tubes. Glass is also critical as a substrate material for photovoltaics, whether it is the large fields of solar cells or these photovoltaic roofs that are being made available by Tesla, for example. Glass is also used as both parabolic mirrors and tubing for solar thermal energy generation. This involves converting solar energy into thermal energy, which then in turn gets converted into electricity. And going beyond energy generation, glass is also a material that can be used for energy storage. So Professor John Goodenough, who recently passed away, he was a Nobel Prize winner, co-inventor of lithium-ion batteries, and up until his 100th birthday or so, he had been working on the design of new glass chemistries for the storage of energy that would enable higher density energy storage, safer energy storage, and greater cyclability compared to existing lithium-ion batteries. Glass will play an even bigger role in healthcare. In addition to being the material of choice for storing vaccines and medicines, glass can provide antimicrobial surfaces for screens that are touched by multiple people. For example, tablets and other screens that are used in hospitals, if they are treated with this antimicrobial surface, which has a layer of ionic silver at the surface of the glass, that can help prevent the spread of secondary infections to help make sure that people don't pick up additional illnesses if they happen to be checked into the hospital. Glasses are also used as bioactive materials. They were initially used to help with hard tissue repair. So glasses can be used to help stimulate bones healing process, for example. They can also be used in dental repair. More recently, a Penn State grad, Professor Delbert Day, who's now at Missouri University of Science and Technology, developed some glass fibers it looks kind of like cotton candy, and it gets packed into open flesh wounds, like, for example, diabetic patients who have ulcers that can be as deep as going down to the bone and simply do not heal on their own. with these new glass fibers, they're actually designed to degrade over a time period of 2 or 3 days, delivering the chemicals that the body needs to heal itself, to regrow the tissue, while also maintaining an antimicrobial environment to prevent the introduction of infection. And the fibrous microstructure here actually helps to stimulate the body's natural healing process, because the way that soft tissue heals itself is by sending out fibers. And so this glass actually provides the framework to help stimulate that process. So we are still at the beginning of understanding how glass can help improve human society going forward in the coming decades and centuries. And I think it's also important to remember that even though as material scientists and engineers, or other types of engineers that we have on this call, we normally think about materials in terms of the engineering properties that they offer and the technical applications they can open up. But glass has been a material of choice as an artistic medium for thousands of years. There are glass beads that date back to Egypt about 3,000 years ago. Glass was known for its beauty, for all the different colors that it can take on, all the different shapes, for its good mechanical performance, for its transparency, for its luster, for its resistance to corrosion when it's exposed to rain, for example. Those are just some of the many reasons why we use glass as an engineering medium, but it also makes it a great choice as an artistic medium. This shows the famous stained glass windows from Sainte-Chapelle, which is in Paris, just outside of Notre Dame Cathedral. This was built over 900 years ago, and it stands today. And the material of glass was chosen here because of all these amazing properties, and it still exists today, almost a millennium later, because of the great corrosion resistance of glass and the great mechanical performance. And so we can admire its beauty, which is in close partnership with all the great engineering properties that glass has to offer. So for all of these reasons, we were really delighted to see that the United Nations had declared 2022 to be the official UN International Year of Glass. This is the first time that the UN had declared any international year for any material. We were a part of a large international team to make this happen, and are very grateful for the UN to recognize all the important ways that glass has brought modern civilization to where it is today, and all the promising technologies that it can enable in the future. So my own personal journey in glass started when I was a young boy, and my parents took me to the Corning Museum of Glass in Corning, New York, and I was immediately captivated by the beauty of glass and all the different colors and shapes that it could take on. I didn't realize it was a valid career choice until I saw this great video from my friendly hometown university, growing up in upstate New York in the Southern Tier. That was Alfred University. Here's a beautiful shot of the campus there in autumn, in early autumn. And I saw this great video from one of the glass professors there, Professor Alexis Clare, who talked about some of these possibilities of glass, and everything really clicked for me. And I still remember meeting her and having the first class with her. She taught me the three most important properties of glass. First, glass is strong. Second, glass is transparent. And third, that glass is fun. And of course, as we learned more, we understood that yes, glass can be strong, but it's not always strong, because if there are flaws introduced, it can actually make the material quite a bit weaker. And also, there are exceptions to the second rule here, that even though most glasses that we think of are transparent, there are many glasses that are not transparent in the visible. They could be transparent in the infrared, or even not transparent at all. So there are exceptions to both of these rules, but no one has ever found an exception to this third rule here. So from there, I started at Corning, actually as a summer intern. while I was still an undergraduate at Alfred. I worked at this campus here. This is Corning's Sullivan Park Research Center, which is just outside of Corning, New York, up on the hill. This has about 2,500 employees, and this is the main centralized R&D center for the entire company. Corning is now the only remaining Fortune 500 company based in upstate New York since the unfortunate demise of Kodak. But it was a really great environment here at Corning for discovering new materials. When I first started there, I was part of the wave of people that they were bringing in to work in optical fiber and photonics. So the first few years of my career were devoted to optical fiber and trying to help to design the profiles of optical fiber and design systems and networks for deployment throughout the country and the world. Unfortunately, what happened was shown here on this graph. This shows a graph of the Corning stock price over time. My first internship here was here in 1999. They hired me back for a second internship where the stock had exploded, basically following this big telecom wave that was kind of a mania hitting Wall Street at the time. Then when I started full-time employment in 2001, the stock had crashed dramatically. In fact, it had gone down to a low of $1.33. So it had fallen from almost 120 down to $1.33. So it had lost almost 99% of its value. And that was a really scary time for the company. Unfortunately, there was huge downsizing. We saw a lot of our friends go. The company almost went out of business. What saved us was actually flat panel displays. So this is around the same time that LCD screens started to become popular, and Corning had invented both the process as well as the glass composition to help enable these increasingly large flat panel displays. And so I really turned the next focus of my attention at work was focused on display technologies for the next several years, on both understanding the physics of glasses being used in these displays as well as the design of glass chemistry. So this is what saved Corning. And following up on that was, of course, Gorilla Glass. And this has been quite a wonderful ride from the design of glass compositions through scale up and manufacturing trials, and then ultimately seeing this product in use by billions of people worldwide. It has been a wonderful ride, and one of the things that I'm pleased by the most with respect to Gorilla Glass is how it has captured the public's imagination as well, where even though conventionally people may think of glass as being a very old material that breaks easily, with Gorilla Glass, that kind of transformed the way that people think about it, that now they can see it as more of a high-tech material that is capable of being very strong. Um, Now, my first interaction with Penn State actually came in 2010. This is at a conference in Brazil, the International Congress on Glass, which is held every 3 years, and it bounces around the world. And they give out this award there. Actually, it's right there. It's on my wall right behind me. The Voldemar A. Weil Award, which is named after the first glass professor here at Penn State, Professor Weil, who was hired back in the 1920s and 30s. He pioneered the science related to glass color. He has a textbook which is still the standard textbook on color in glass. And all of that work was done right here in this building where I get to work. And in fact, I've inherited his PhD regalia, which is in a cabinet behind me here. But I was presented with this award in his honor, and the presentation was given by the current glass professor at Penn State, Professor Carlo Pantano, who's shown here on the right. He worked here for, I think, 37 years as a glass professor. He was the director of Penn State's Materials Research Institute. If you've ever been here and seen the Millennium Science Complex, it's because of him that happened. That was his vision. He's the one who brought that into existence. So his impact on glass was huge, and his impact on the Penn State campus was even much broader than that. So he invited me out for breakfast that morning, and started the conversation about, hey, have you thought about becoming a professor? And anyway, he planted the seed there. And when I got back to Corning, we were discovering that it was becoming increasingly difficult to hire well-qualified people in glass science and engineering, because a lot of the professors that my colleagues and I had learned from had retired or were retiring, and they weren't necessarily being replaced by glass people, presumably because of this notion of glass being an old-fashioned material. And so we actually did some studies on this to find out what was going on. What you see in this graph is a plot of the number of scientific papers being published in glass as a function of time. And the different lines here are from different countries. And what you see is that the United States was on the top here throughout most of history, but our research output in glass science peaked in the mid-90s and kind of remained flat or even started to decrease a bit. Among Japan was in the number 2 position right behind us for a long period of time, but they actually suffered a bigger pullback in glass science starting in the late 1990s. Western countries like Germany and France and so on, very similar trends. Meanwhile, China came from nowhere. They had 0 publications in 1960. They came out of nowhere and invested heavily in glass science and technology. And they have been experiencing exponential growth as a result of that. And nowadays, they more than double the research output of the United States in this very important material. So, we were very concerned both for our own company as well as more broadly the well-being of, especially the long-term well-being of the U.S. glass industry. So we tried to do whatever we could to help convince, the National Science Foundation of the importance of funding research in this area. The company itself was investing and sponsoring research at universities. We pulled together a Corning Glass Summit. We created a scholarship for students called the Corning Glass Age Scholarship. We did everything we could to think of that we could think of. And then one day we found out that Professor Pantano from Penn State was planning to retire, and we had hired every one of his students for the past decade. And I still remember being at a meeting at Corning with our director of university engagement saying, Carlos retiring, what are we going to do? And anyway, my former boss there told me that I took the problem a little bit too seriously when I quit my job there and came here to become the next professor of glass science here at Penn State. And what I found is really the perfect place to study glass. The department here is outstanding. The college, the whole university and Happy Valley environment. It's just an amazing place to conduct glass research. In fact, here's a partial group photo. This was actually taken in my hometown of Alfred, New York. One of my former students is now a professor at my alma mater at Alfred University, and he's already got the second largest group at that entire university, and is doing just a transformational job there for them. And he organized a conference there called the University Conference on Glass, and I was really delighted to bring a pretty big fraction of my group from Penn State back up to my hometown to see the sites and to have a lot of great discussions about glass. So everyone here is, coming from different backgrounds. They're coming from different parts of the country or different countries around the world. They're coming from backgrounds in material science or physics or chemistry or chemical engineering or even art. But they all share this common love of glass that brings them together. So let me give you just a brief overview of who's who in my group here at Penn State. We've very quickly built by far the biggest and the broadest academic glass research group here in the US. I'm very fortunate to have these 3 research staff members working closely with me. Especially to help lead the group. Dr. Hongyan Kim, who got his PhD here at Penn State, he actually lives in Pittsburgh because his wife is a professor at Carnegie Mellon, and he leads a lot of our theoretical and modeling and simulation research. Dr. Nick Clark, who I first met as an undergraduate student when I first came here. He did his PhD with me and is now a postdoc, and he is leading our experimental glass research efforts on LionGlass, which I'm going to talk about at the end of this talk. Dr. Maziar Montezerian, who is a professor in Brazil, and he has been with me now for over a year as an assistant research professor, and he has extensive background in bioactive glasses, glass ceramics, and crystallization behavior. We've got a wonderful group of PhD students here. Elif is coming to us from actually the Turkish glass industry, and she is studying recycling and color compatibility of LionGlass. She's been working closely with Bob and Pete here, and really devoting her PhD studies to what is the best path forward to enable recycling of our LionGlass composition, which will be the focus of the latter part of this talk. Shaylee is a Pennsylvania native, a graduate of Penn State. She had 3 years of experience in the polymers industry before coming back to get her PhD, and she is working on polymer coatings on glass. Aaron comes to us from Wisconsin. He's working on a project with Corning related to glass relaxation behavior. He's also a glass blower, and he is the manager of our glass blowing studio, which is in the next building over. And he is very passionate about STEAM, STEAM education, so science, technology, engineering, art, and mathematics. And the glass blowing studio that we have here has been a wonderful way to help get the word out about glass, get people excited about glass, while also demonstrating many of its important engineering properties. Yuki she's pursuing a PhD in chemistry. She's working on bioactive glasses as well as photothermal effects in ceramics. Chang is working on molecular dynamics simulations of crystallinucleation after having finished his master's degree here at Penn State. Brittany comes from Coe College in Iowa. She's got a double background in physics and art, and she's working on thermal properties of glass and is just about to finish up her PhD. Bahara is a chemical engineering PhD student who is focusing on zirconia glass ceramics to help improve the toughness of glass ceramic products. Mason is working on fundamentals of nucleation and crystallization. Mehmet is working on LionGlass for architectural and hollowware applications. Christian is working on fiberglass and basically studying how fiberglass can interact with the melting refractory in the glass melting furnaces. Titus, he's actually an 8-year veteran of the Navy, and he is toward the tail end of his PhD. He's working on cementitious materials and also on LionGlass. Adam comes from my hometown area and is a graduate of Alfred University. He is studying infrared transmitting oxide glasses on a Navy project. Jessica comes from Idaho and she graduated from Washington State. She's looking at the fundamental science of glass corrosion and how we measure glass corrosion. And Danchi is working on hollow glass microspheres. Also in the group, we're very fortunate to have a number of undergraduate researchers shown here. Penn State is actually really good at getting undergraduates involved with research. Elizabeth and Julia have been very critical for our LionGlass efforts. Olivia and Allison are both working on bioactive glasses along with Daniel. Sophia is here, and this is her first semester, and she's into glass science as well. And Nathan and Brandon have been helping out with a lot of our glass characterization. So what is it that makes glass so interesting? It gets back to where glass comes from. So glass comes by cooling a liquid from a melt, where that melt is cooled so fast that it doesn't crystallize. And kind of the main physics behind glass is that if you start off in the liquid state, normally if you cool a liquid, it will crystallize. It'll undergo this first order thermodynamic phase transition as the atoms in the liquid and the disordered liquid rearrange themselves into an ordered crystalline configuration and form a crystal. This is what happens in equilibrium. However, crystallization takes time because it takes time for the atoms in the liquid to flow into just the right arrangement in order to form that crystal. And if you cool the liquid fast enough, you can actually cool it so fast that you can avoid crystallization. And when that happens, you get what's called a supercooled liquid. A supercooled liquid is a metastable state that refers to any liquid that is cooled below its normal freezing point. And if you take that supercooled liquid and you continue to cool it, the viscosity of that supercooled liquid continues to go higher and higher. So it becomes less and less fluid. It's taking longer and longer timescales for it to flow. And eventually the time scales for it to flow become much longer than our time scales of observing the supercooled liquid. When that happens, it undergoes this so-called glass transformation range or glass transition range, and you get a freezing in of that supercooled liquid structure. So you get a material that for practical purposes behaves like a solid. Mechanically, it behaves like a solid, it breaks like a solid, but it has the structure of a supercooled liquid. And that is what we all know and love as a glass. And glass is a thermodynamically unstable system. It is continually trying to relax towards the supercooled liquid, and the supercooled liquid is in turn metastable with respect to the crystal. And so if you wait an infinite amount of time, the glass is going to relax towards the supercooled liquid and then undergo a phase transition to crystallize. So what we're observing in the glassy state is inherently a transient material. It is an out of equilibrium material. It's characterized by its non-crystalline disordered structure, its non-equilibrium thermodynamics. The relaxation towards the supercooled liquid follows this complex non-exponential pathway. It is what's called non-ergodic, which implies that the timescales of this relaxation process are very long. And even though glass is a very old material, it's at the forefront of material science because a lot of the conventional theories that we learned in school are simply not applicable to glasses because you can't just take standard equilibrium thermodynamics or standard crystal chemistry and apply that to glass because glass is its own thing. So some of the highlights from my research career, one of the areas of my research has been in what's called the statistical mechanics of glass. Statistical mechanics is a field of study that was invented by Ludwig Boltzmann back in the late 19th century. This is a bust of him at his gravesite in Vienna. And this was actually really controversial when he first invented this, because at that time, it was controversial that materials were even made out of atoms. A lot of the prominent scientists at the time didn't believe that. And Boltzmann was proposing that not only were materials made out of atoms, they can exhibit different types of configurations with different probabilities. And the properties that we observe and at the macro scale, the thermodynamic properties, the mechanical properties, and so on, can be described in terms of some sort of suitable averaging over these atomic configurations that the materials experience. And this was highly controversial for a couple of reasons. First was that he was building it on this controversial notion of materials being made out of atoms. But secondly, he was building in probability theory into physics. And at the time, probability and statistics were considered to be an immoral branch of mathematics because the only thing that they were good for was gambling. And so he was got treated horribly in the community. He unfortunately took his own life. He was buried and his work was forgotten about for about 20 years until another famous scientist, Max Planck, realized that Boltzmann was right and revived his work. The good people of Vienna actually dug him up and gave him a much better grave, as shown here. And I was really, really touched when one of my former students, Jonathan Balog, actually took my book. This is my kinetics book here. he took it with him. I talk a lot about Boltzmann in this book. He took this book with him on a trip to Vienna and sort of offered it here at the gravesite of Boltzmann. So that was really touching for me. And a lot of my work has been taking these theories that were initiated by Boltzmann and then applying them to these non-equilibrium systems such as glass, where the disorder of the glassy state means that we don't know exactly where the atoms are. We only know where they are with certain probabilities. And so all the stuff that Boltzmann developed is really intrinsic to the glassy state and has been the subject of a lot of work from my group. Another major area of research has been in what's called energy landscapes. If you think about walking through the beautiful mountains out here in Appalachia, you can walk along the valleys, walk up the mountains, and so on. If you think about your elevation as being like, what is the energy of the material? Certain regions are really unstable, like at the top of mountains. Areas that are lower energy in the valley are more stable. And we can think about materials in the same way, that there are certain configurations of the atoms in the materials that are more stable and have a lower energy that are in the valleys, and then ones that are less stable that are at the peaks of the mountains here. And we can actually describe a lot of the thermodynamics and the kinetics of materials in terms of this energy landscape description. And a lot of my work has been developing both the basic theory of this as well as the techniques to kind of walk through this energy landscape, discover the different configurations that materials can adopt, understand what's the likelihood that they're going to occur, and then see how they're going to influence properties. Another major focus of my research has been on the viscosity of glass-forming liquids and glasses themselves. This plot shows the logarithm of viscosity as a function of an inverse temperature here, where if you take a liquid and you cool it, you're moving to the right here on this graph. The viscosity is increasing by orders of magnitude. So it's kind of like water here, and as you continue to cool it, it becomes like honey, and it becomes thicker and thicker, more and more viscous. And eventually it becomes so viscous that it becomes essentially frozen in. When that happens, you get this departure from the equilibrium curve, and then you get the glassy state here. And so a lot of my work has been actually developing the equations to describe both the viscosity of the liquid state, the so-called Maega equation, and the viscosity of the non-equilibrium glassy state, the so-called MAP equation. And I got to check off one of my life goals here when I found out that one of my equations, the Maega equation here, was actually incorporated into some standard plotting software Origin Labs. So that was kind of cool. Another area of research is what's called topological constraint theory. And the way that you can think about this is that any material, including glasses, is made up of atoms, and these atoms are connected to each other by bonds. The topology of that network is basically what's the connectivity of these atoms with each other. And what we can do with this topological constraint theory is relate that connectivity of the atoms back to the properties that we care about, such as the annealing point of glasses, for example. And so a lot of work has gone into developing this theory, applying it to different properties, as well as applying it to different families of glass chemistry. When it comes to glass relaxation, so glass relaxation is the slow approach that glass takes to try to get back to the liquid state. And this can be measured. It can be measured even for high-tech glasses like we developed at Corning, like Corning Eagle XG and Jade glass, which are used in your flat panel displays. What you can see here is that the viscosity of either Eagle XG on the left or Jade on the right, it is initially has this lower value, but then over time, if you hold the glass isothermally, either at 600, 650, or 675 degrees C, or at these higher temperatures for the glass on the right, over time, the glass is relaxing. Over time, the atoms are slowly moving. They're slowly approaching the liquid state. And as they do that, all the properties of the system change, including its viscosity. And here you can see that over time, the viscosity is increasing, and it's increasing by 1 to 2 orders of magnitude. So it is undergoing enormous changes. And this requires very precise measurements experimentally, as well as some fairly sophisticated theories to make the model predictions. Sometimes we get to have some fun too. And one of the fun projects that we did was to address this problem or this question of cathedral glass flow. Maybe some of you have heard this urban legend that that the stained glass windows in old cathedrals are flowing over time, and that if you look at the bottoms of the stained glass, that they're a little bit thicker at the bottom compared to the top. And some people have assumed that that is because it's flowing over the centuries. So we actually decided to try this out. Working with one of my friends from the Corning Museum of Glass, we got the composition of Westminster Abbey glass, and we made our own medieval cathedral glass using their recipe, using the medieval recipe, and then used our modern models and characterization techniques to get the viscosity of this medieval glass. And at equilibrium here, it is the black line. The model in non-equilibrium predicted the red line, and the measurement here, the lowest temperature measurement we got was in the blue point right there. And the viscosity actually was quite a bit lower than what had been previously estimated back in 1999. The room temperature viscosity of medieval glass is 10 to the 24.6 Pascal seconds, which is about 16 orders of magnitude lower than the previous estimate. But it turns out that it's still too high for the glass to actually be flowing at room temperature. This graph shows that basically, if you were to wait a billion years, yeah, the glass is flowing, but it only flows by about a nanometer. So the increased thickness that is observed in some stained glass windows is not because the glass is flowing, but rather the medieval methods for making glass were based on spinning a gob of glass out into a disc and then cutting that up into little pieces. That's called the crown process. And basically that leads to some intrinsic thickness variations. And it's only natural then for the stained glass artisan to put the thicker part on the bottom because that at least gives the appearance of being more mechanically stable. Another thing that we do quite a bit of is designing new glass compositions. Um, we have this thing called decoding the glass genome, which is basically trying to go from our periodic table here, where there's an infinite number of possibilities for potential glasses that could be made because of this periodic table. Just about anything could be put into a glass, except for the noble gases here. That doesn't mean you'd want to put it in. There's a lot of things that are either radioactive or toxic, or they would change the glass into a color that you don't want, or they're ridiculously expensive. There's all kinds of reasons why you wouldn't want to use a lot of these elements. But in principle, there are an infinite number of glasses because of their non-crystalline structure. You don't have to obey those rigid rules of stoichiometry that are required in crystals. And what we want to do is figure out an effective, efficient way to go from these infinite possibilities to using what we know about the structure of glasses to predict what the optimized glass would be to get the properties that we desire. One of the places where we've used this a lot has been in the design of chemically strengthened glasses like Gorilla Glass. The way that Gorilla Glass works is that the glass is designed to have a large amount of sodium in it. And then the glass, as formed, gets submerged in a molten salt bath, where that salt bath has a larger alkali ion. It's usually potassium nitrate. And this is done at temperatures of about 400 degrees C. So the glass has a lot of sodium in it. The salt bath has a lot of potassium. It's submerged in the salt bath for about 8 hours. And over time, this is driven by entropy. The sodium ions hop out from the glass into the molten salt. They're replaced by the larger potassium ions from the salt bath. And it's kind of like if you think about these sodium ions as being, I don't know, golf balls or something. You're taking golf balls out and then you're trying to stuff tennis balls in, and the tennis balls don't quite fit. And so what they want to do is they want to expand the surface structure of the glass a bit but the surface is bonded to the interior of the glass, which doesn't allow it to expand. So if the surface wants to expand, but it's not allowed to, that actually creates a compressive stress layer in the surface. And this compressive stress is on the order of a gigapascal. So now if you want to break a chemically strengthened glass like Gorilla Glass, you have to overcome not only the intrinsic strength of the glass, but this additional 1 gigapascal of the compressive stress layer. So it becomes a lot more difficult to break the glass that way. And when it comes to the design of new glasses, um, there's always a set of properties that we want to try to meet. These product-facing attributes like the ion exchange properties of Gorilla Glass, for example, and the resulting damage resistance, its chemical durability, its density, its hardness, and so on. All of these properties that are needed to meet the requirements for the application and to be superior to whatever competitors are offering. But that's only half of it, because the other half is the set of manufacturing attributes that customers of the glass industry, end users, they don't see these, they don't care about these, but they are essential if you want to be able to manufacture the glass with consistently high quality, um, low enough cost, um, having good sustainability with respect to your melting tanks, forming equipment, and so on. And what makes this challenging is that anytime you change the composition of the glass, it's not just one of these properties that changes, but all of the properties are changing together. And so using this kind of concept of decoding the glass genome, what we have done is to develop predictive models for these different properties that we care about, and stitch them together so that the design of new glass compositions can be kind of predictive from a modeling point of view. This is an example of actually one of the Gorilla Glasses that have been developed, that dramatically improved the damage resistance of the glass. Here, what we wanted to do was maximize the property that we cared about the most, which was the damage resistance. We did that by adjusting the chemical composition of the glass. You'll note that silica is missing here, and that's because not all the components are independent of each other. Silica is just 100% minus the summation of everything else. And then it's subject to the constraints on all the other properties that we care about from both a product facing point of view as well as a manufacturing point of view. And if the models are working well, this should spit out the formula for the optimized glass. And in fact, that's exactly what was done here. This glass went on to sell billions of units. You can see this is the performance of an older glass under a 0.5 Newton scratch, where you can see this lateral cracking, which not only looks bad and feels bad, but greatly compromises the strength of the glass, versus the new glass with improved damage resistance, which actually is just deforming plastically under the indenture here at an even higher load. Our group is also working on glass ceramics. So glass ceramics are glasses where we have purposely grown some sort of crystalline microstructure. You probably know of glass ceramics from, like if you've got a smooth glass cooktop, that glass cooktop is actually a glass ceramic cooktop, because the crystals are helping to change the thermal properties and the mechanical properties to be able to withstand these huge temperature differences and kind of banging of pots and pans on the stovetop. You might also be aware of glass ceramics from Corningware. So Corningware is also a glass ceramic. A lot of dental inlays are glass ceramics as well. And we're developing tools to help to understand the microstructure of glass ceramics and be able to predict its properties. For example, we're working with a dental glass ceramics company now, and they care about being able to have glass ceramics that can be made in different shapes to match whatever the individual patient needs. Also be able to have the hardness and the toughness and the chemical corrosion resistance that normal teeth have. Because if you're drinking, say, a highly acidic beverage, we have to make sure it doesn't dissolve in that. Also, if the glass ceramic is too soft, it'll get damaged. But if it's too hard, it'll damage your natural teeth. So it has to be, the right level of hardness, and it also has to have the right color and the right translucency. So teeth, as much as a lot of those commercials would like to convince you otherwise, teeth are not white. Teeth are naturally off-white, and we have to be able to reproduce that natural color. And there's actually a gradient to the color of teeth too. They're actually slightly darker at the root and become lighter in color towards the tip of the tooth. And there's a little translucency to it as well if you look at the places where it becomes thin. And so it's really important to be able to capture all those effects in order for it to be realistic. And glass ceramics are the medium of choice for that. Finally, we've also been working on some designs for next generation optical fibers that show how you can reduce the Rayleigh scattering and optical fibers by putting them under pressure and by making them under pressure. This changes some of the fluctuations that exist in the glass and can actually help to enable next generation optical fiber. And we're also working on some really crazy new glass chemistries. The newest, completely new family of glass chemistries is what's called metal organic framework glasses. This is actually a hybrid glass that is part organic and part inorganic. And this is the biggest piece that has ever been made to date. It's only 5 millimeters across. But this is interesting because it actually forms a relatively stable glass, and it combines some of the properties of inorganic glasses and polymers. So this is just very much in its infancy. My group also has a whole bunch of software tools that are all available through our website. They're all open source, they're all free. And so you're welcome to help yourself to any of these. These help to model the relaxation behavior of glass, map out energy landscapes, study how glass properties evolve with time, aid in the composition design of glass, study the surface chemistry, study the structure of glasses. All of these tools are freely available. Now, I'd like to spend the last part of my talk to tell you about one of our most exciting new projects, which is LionGlass. The problem that we're trying to address here is the carbon footprint of the glass industry. As happy as I am with all the cool work that we did at Corning and how successful things like Gorilla Glass have been, the fact remains that Gorilla Glass is a tiny part of the overall volume of glass that is being manufactured worldwide. The vast majority of glass that is produced is standard soda-lime silicate glass. This is the glass that is used for all architectural windows. It's used for all drinking glasses. It's used for wine bottles, beer bottles, beverage containers, food packaging. It's used for automotive glazing. It is ubiquitous, and it has not changed in a very long period of time. And the glass industry had kind of gotten itself into a bit of a catch-22 because companies like Corning that have higher profit margins and can invest a lot in research and development aren't interested in getting into lower margin commodity industries like soda lime. The soda lime industry doesn't have the profit margin to be able to invest in the type of transformational research that is required to make a substantial change away from soda lime silicate. So we found ourselves in a pretty nice position here at Penn State in having the equipment, the expertise, and the knowledge to make it happen. So the glass industry still produces over 86 million tons of carbon dioxide each year. This is predominantly due to soda lime silicate glass. About 70 to 80% of that is due to the energy consumption from the high temperatures required to melt soda lime silicate, which is about 1450 to 1500 degrees C. The remaining 20 to 30% is from decomposition of carbonate batch materials. It's called soda lime because two of the main ingredients are soda ash, which is sodium carbonate, and limestone, which is calcium carbonate. When they're melted, they first decompose into oxides. When the carbonates decompose into oxides, they release carbon dioxide in the process. And so LionGlass is our alternative to soda lime silicate. This is named after our Nittany Lion mascot here at Penn State. And what it does is it reduces the melting and forming temperatures of glass by about 400 degrees Celsius compared to standard soda lime silicate. It also eliminates the use of carbonate batch materials. So, for example, the upper table here shows soda lime silicate. What happens when you melt a 125-gram batch of soda lime silicate is that the carbonates decompose into oxides, and they release 24.1 grams of CO2. It's a huge amount of CO2 for that small batch compared to LionGlass, which eliminates the carbonates. The only CO2 here is due to trace impurities or CO2 that was already in the atmosphere. And so for the same size batch, it only releases 0.3 milligrams of CO2 from the batch to melt conversion process. It also dramatically reduces the energy consumption and associated costs and carbon footprint because of that temperature reduction. Another nice thing about LionGlass is its improved mechanical performance compared to soda-lime silicate. The upper right plot shows the probability of soda-lime silicate glass cracking under an applied force, under a Vickers diamond indenter. The crack initiation threshold occurs at this 50% crossover, which for soda-lime is about 1 or 0.1 kilograms force. So here you've got a 50% probability that the glass is going to crack. And then if you go above that, it quickly becomes 100%. With LionGlass at 0.1 kilograms force, that's got a 0% probability of cracking. And in fact, if you go 10 times that high, which actually maxed out our equipment here, to 1 kilograms force, it's still just a 25% probability of cracking. So the damage resistance is at least 10 times higher for LionGlass. And this improved damage resistance can be a pathway towards lightweighting of glass products, especially hollowware, glass packaging. The reason that the glass is still so thick is for its mechanical performance. And if you've got a new material that is intrinsically better in that respect, you could trade that off by going to thinner walled jars. And lightweighting has a number of advantages because that's reduced materials consumption, that's reduced energy consumption again, because less material needs to be melted. It also lowers the transportation costs and the energy associated with transportation. And one final advantage of LionGlass is that it absorbs more radiation in the near ultraviolet. So if this is used as packaging for anything that is sensitive to UV degradation, like any number of beverages or food or cosmetics products, then there can be some additional protection there optically from LionGlass. You can also, even though LionGlass is clear, it's actually clearer than standard soda lime. You can make it all the same different colors, just like you would with soda lime silicate. So it's also really fascinating as an artistic medium. One of the nice things about doing this as a side project with no official funding is that Penn State owns the entire intellectual property without any strings attached to any companies or government agencies. And so we've filed actually 2 patent applications now on 2 generations of LionGlass. The first patent application is published, the second one hasn't published yet. And so this actually puts us in a really good place with respect to intellectual property. Going forward, I've been asked many times about, my startup company or whatever. I personally am not interested in doing that. I love my job here at Penn State. I've had enough of working in industry. And I want to focus on my academic career and teaching the next generation of students. And I also don't think it makes sense to have a startup company for something like this because the amount of capital investment that's required to make glass is enormous. Moreover, I don't want this to be seen as a threat to the glass industry. I want this to be seen as an opportunity and something where we can work together with them. And so our plan is, what we're doing is licensing our intellectual property directly to existing glass companies with the goal that this is kind of like what Gatorade is to University of Florida. We want LionGlass to be like that for Penn State, so we can get some royalties and then use that to help have scholarships, to help support research, and hopefully create a virtuous cycle here. We've been working together with a small company in the Netherlands called Celsium to do some melting studies. They have a really nice setup where they have a transparent crucible. We can put your batch materials in there, in the transparent crucible, in a furnace. There's a window going into the furnace with a CCD camera to take videos. And the furnace, the exhaust here, is hooked up to a gas chromatographer to measure all the gases that get released during the glass melting process. This shows a picture of their setup with the furnace here, the window, the camera. And then this video shows the fining process of soda lime silicate. Fining is just the removal of bubbles as they rise up to the top. And then this video on the right, this shows the batch to melt conversion process for a standard soda lime silicate. The temperature in the upper left is the current temperature in degrees Celsius. You can see not much is happening, at least visually here, even as we get close to 900 degrees C. Here it's we're starting to see a few reactions, but it's kind of slow coming. On the left, you can see the gases measured by the gas chromatographer. The CO2 is actually divided by 100 here just to fit on the same scale as everything else. If you integrate the CO2 here, you get a total of 24.1 grams of CO2 released for this 125 gram batch. Then at these higher temperatures, there's sodium sulfate that's included. That is what's called a fining agent that actually releases more bubbles to increase the size of the bubbles so they rise to the top faster and you can get rid of them faster. And so here, as we get to, let's see, 1250 degrees C, you can see that there's still a lot more work that needs to be done for melting this batch material and getting a nice homogeneous glass. As we get to 1350, you can see more of the bubbles are evolving here. As we get to 1400 degrees C, the fining agents kicking in. We've got SO2 blisters that are being released. They're increasing the size of the bubbles. The viscosity is going down so the bubbles can evolve to the top. And as we get to 1500, everything calms down and you get a nice homogeneous glass here around 1500 degrees C. This shows the same thing for LionGlass under the same setup, the same size batch. The movie is showing the batch to melt conversion of LionGlass here. We're just above 650 degrees C. You can actually start to see some of the reaction kinetics even at 650 degrees C. As we get to higher temperatures, the kinetics become faster. They operate over larger regions here. The gas chromatography results are shown on the left. Now the CO2 is just the CO2. It's not divided by anything. And if you integrate that, that's just 0.3 milligrams of CO2. Instead, the primary gas that gets released is actually water vapor. This is the water vapor concentration divided by 1,000. Comes out to, I think it's like 8 point something grams of water vapor that gets released in this LionGlass batch. And so the water vapor is actually helpful for creating the bubbles and making sure that we get good homogenization of the glass melt. But we're trading in something that's environmentally harmful, CO2, for something that's environmentally neutral here with H2O. Now, as we approach 900 degrees C, look at this. You get this bubbles rising up. This is very similar to what we saw in soda lime at 1400 degrees C. And as we get above 900, we're getting closer to 950 degrees C. Things are starting to calm down. This is like what we saw at 1450 degrees C in soda lime. And then as we get to 1000 degrees C, we've got a fully fined, really nice quality homogeneous melt here of LionGlass, all at 1000 degrees C. So that was actually 500 degrees C below soda lime silicate. This is my student Aaron, who's in charge of our glass blowing studio, and this is the first ever blowing of LionGlass. This wasn't the greatest quality melt, but the properties that are required for blowing of glass, control of the viscosity curve and so on, are actually very similar to the properties required to make glass packaging, for example. And he's using our art tools here to demonstrate the engineering properties of the glass. The other thing that you'll note here in this video, go back and forward here, is that it's not glowing at all. And that's because the temperatures are so much lower with LionGlass. So, it's safer from the point of view of, your eye protection and thermal protection too, because of the lower temperatures that are involved. And this is a glass flower made out of LionGlass. This was made by my postdoc, Nick. And so we're getting quite a bit of excitement from the art community as well. This has really taken off. We got featured in BBC World News. We got to go on the Fox Big Ten kickoff here. This is my undergrad student, Julia. We got to meet the governor here. So it's been a lot of fun. And I don't know if you've watched any of the Penn State football games on Big Ten Network, but for the Penn State games, they've been showing this at halftime, which is really cool because it features our department, our college here at Penn State, and it's another way, much like we had with Gorilla Glass, of really getting the word out there to the general population about the excitement of glass and the fact that you can come here to Penn State and really be at the forefront of all of this. And so that, even by itself, I think is a big win. For some people have had some other ideas about what we're doing, other conspiracies here, like reforging the One Ring. I will neither confirm nor deny that. Most recently here, we've had our first partnership with a glass company. The first one on board is Bormioli Luigi. They are an Italian glass company based in Parma. They make a lot of the glass packaging that is used for cosmetics, high-end cosmetics packaging. And this shows some of their products here. You can see some of their customers, Prada, Chanel, Dior, and so on. Chanel has actually told us explicitly that they would like the next generation of Chanel #5 to be packaged in LionGlass because their customers care very much about going to greener packaging. We're also in discussions with a French glass company. We're getting close to an agreement with them for high-end spirits packaging. Both cosmetics and spirits packaging are really good entry points because they are higher margin compared to most of the commodity glass industry. So, more resources can be spent to help with the engineering and scale up. Also, they're smaller volume compared to some of the others, so it's good to kind of establish ourselves there first and then go to larger markets. We're also in discussions with a major flat glass producer that is fairly local here, and hopefully we'll have some news about that early next year. For now, I want to thank you very much for your time. I hope you enjoyed the talk, and I'm happy to take any questions that you may have. I'm going to stop sharing my screen so I can see what's going on. All right, thanks everyone.
Okay, Dr. Morrow, thank you for that very informative presentation. We are now going to field some questions for Dr. Morrow. Again, if you have any questions, please enter them using the Q&A feature located at the bottom of your screen. So the first question, Dr. Morrow. Can lime glass be recycled? And if yes, can it be mixed with standard soda lime glass?
Great question. So my PhD student, Aleph, is working on exactly that question. And we're getting a lot of help from Pete and Bob. In fact, they arranged for visits around different recycling facilities in the tri-state area here with Pennsylvania, New York, and New Jersey, and seeing what is done in recycling facilities. The key thing is to sort. We need to be able to sort LionGlass to separate it from soda lime streams. Currently, there is X-ray fluorescence equipment that is used to, for example, separate lead silicate from soda lime silicate. One of the things that we're working on is creating an XRF standard that can be used to help identify LionGlass in the XRF equipment so it can be separated from soda lime silicate. Another way to separate it would be optically, and this is based on the difference of the UV transmission and the near infrared. Basically, this would be an extension of what's done now to separate different colored glasses. The difference is instead of probing the glass with a laser in the visible spectrum, it would be in the near UV. So those are the two most promising paths right now to sort out LionGlass. If you mix it, what happens? LionGlass and soda lime melt at very different temperatures. And so one of the things that Aleph is doing is to see how much contamination of one can the other take. We're in the early stages of that. I anticipate the answer is going to be that we can tolerate some small amounts of contamination, but there will be a threshold where beyond which you start to get quality issues. And so Aleph is going to figure out at what point do problems start to arise? What can we do with the LionGlass design to help maximize the use of soda lime cullet? And also, what are the best strategies for helping to sort LionGlass from other types of glass in the recycling stream? So to answer your question directly, yes, LionGlass is recyclable, but the big challenges are in basically managing those recycling streams, as you probably know.
Okay, thank you. Next question. Can LionGlass be crushed and used for sand and aggregate in construction, and will it pass those standards?
I believe, yes, it will be able to be used in that application. We have not tested it against those particular standards, and so we would need to do that to be sure of that. But yes, I do believe that could be another option for the end of life of LionGlass products to be crushed up in that manner.
Okay, and probably the last question to wrap up the session. Can types of industrial waste such as slag and ash be added to LionGlass in its, in its composition? As like a filler, I guess you could say.
I don't think so as currently designed, although that is an interesting question to consider for the future. So yeah, currently no, unfortunately. But yeah, we'll need to keep that in mind for potential future developments.
Okay, that'll be it for the questions. So again, this webinar, like all webinars in this series, has been recorded and will be available via YouTube links on both the National Recycling Coalition and Recycling Market Center websites. Thank you again for joining us. We hope you'll join us for future webinars. Please visit the NRC and RMC websites for schedule updates.
Great. Thank you, everyone.
Thank you. Have a good day.
Yeah. Bye-bye.